In this video, I want to solve a sample word problem related to mechanical vibrations. So our problem says the following. A 5 kilogram mass stretches a spring by 3.77 meters. Assume that there is a dampener attached to the spring with coefficient of 2 newton seconds per meter. If the mass is pulled down by an additional 0.3 meters and given a downward velocity of 0.5 meters per second when released, find a function for the position of this mass over time. Rounding there, so find the spring constant. How do you describe the damping? Then find a time t such that for all time t bigger than capital T, mass within 0.001 meters of equilibrium position. All right, so to get started on this, we want to figure out what coefficients we have in our problem, what we don't have, and what we can solve for. If we go through the problem statement, we can see we were first told what the mass is. We have a 5 kilogram mass. That means that for our problem, the mass, m, is 5 kilograms. We're going to be in kilograms, meters, seconds, units here, so the units are all going to be fine. We are also told that we have a spring that has a dampener on it with coefficient 2 newton seconds per meter. So we know that our damping coefficient gamma is going to be 2 newton seconds per meter. We're also given an initial position of being pulled down by an additional 0.3 meters and downward velocity of 0.5 meters per second. What that means is that we're going to have for our conditions, we will have y of 0 equals 0.3 meters. Here using the convention that the downward or extension direction is positive on the spring. And then our velocity, y prime at 0, will be 0.58 meters per second. That's all we're told. But we're missing something here. We're missing k. We will need the spring constant to write the diff EQ, that we can then solve to figure out the trajectory here and the position over time. How do we find k? Well, there's one factor we haven't used yet, and that's this 3.77 meters. So because the mass stretches a string by 3.77 meters, our basic physics knowledge can take over and tell us that for this situation, we know that mass times acceleration due to gravity is the spring constant times the length of spring extension. Mass at equilibrium, it's not moving, so the gravity force is canceled out by the spring force. That's the equation here. And so we have that 5 kilograms times 9.81 meters per second squared should equal k, our spring constant, times this length of 3.77 meters. Therefore, k is 5 times 9.81 over 3.77. And if you round this to the nearest whole number, you will get 13 newtons per meter. That means we now know what our k is, and our k is 13. So from that, we can now write the initial value problem that our position here is going to solve as a function of time. And that problem is 5y double prime for the mass term, plus 2y prime for the drag term, plus 13y equals 0 with initial conditions, y of 0 equals 0.3, y prime of 0 equals 0.58. All right, now that we have that, we just need to solve it. How do we solve these kinds of problems? We do our guessing of e to the rt, and that's going to result in the quadratic that we have to analyze. 5r squared plus 2r plus 13 equals 0. And we want to find the roots of that. With that 5 in front, I'm not going to factor this, so just quadratic form this and see what happens. So we know that r is negative 2 plus or minus the square root of b squared, which is 4, minus 4 times a times c, 4 times 5 times 13, all over 10. Negative 2 plus or minus square root of 4 minus, that's 4 times 5 is 20, times 13 is 260 over 10. Inside the square root, I will see negative 256. So I will have negative 2 plus or minus I square root 256 over 10. 16 squared is 256. So this is negative 2 plus or minus 16i over 10, or negative 1/5 plus or minus 8/5 I. Now that I have that, I can write out my general solution. So because those are my roots, I know that my solution is going to look like c1 e to the minus 1/5 t, or a t over 5, cosine of 8/5 t, plus c2 e to the minus t over 5 sine of 8/5 t. Cool. We also say right now, because these were complex roots, we know that this will be an underdamped situation. Complex roots, b squared minus 4ac is negative, we're underdamped. But now if I want to solve the initial value problem, I need the derivative of this function, so I can plug 0 into both y and y prime to find c1 and c2. So you compute y prime here, and each term here will involve the product rule. That's what we get for y prime of t. Take your time, 2 product rules, it works out all right. Okay, now I want to plug in t equals 0 to both and use that to use my initial conditions to then find c1 and c2. So it will have that y of 0. Well, if I plug 0 in for y, the sine term just goes to 0, and so it's gone. Exponentials go to 1, cosine goes to 1, so I just get c1 here. And y prime of 0, both sine terms are also gone, so I'm left with negative 1/5 c1 plus 8/5 c2. I know that I want y of 0 to be 0.3, and y prime of 0 to be 0.58. I can now solve for these. So here I get that c1 equals 0.3. Plugging that into the bottom equation, 0.58 equals negative 1/5 times 0.3 plus 8/5 times c2. I'm just going to multiply through by 5 to get rid of those denominators. So I end up with a 2.9 equals negative 0.3 plus 8c2. So 3.2 equals 8c2, or c2 equals 0.4, which lets me then write my solution. So my solution will be y of t equals c1 0.3 e to the minus t over 5 cosine of 8/5 t plus c2 0.4 e to the minus t over 5 sine of 8/5 t. So that represents the position of the mass on a spring as a function of time. We already said it was underdamped. What else do we have to solve for? Find the position, good. Whole number, great. Dampening, got it. Find a time capital T such that for all little t bigger than t, mass within 0.001 of equilibrium. So we're on to this last part here. How do we go about doing that? Well, that is the envelope curve part of this problem. What we want to figure out here is a capital T such that if t is bigger than that, the absolute value of y of t is less than 0.00001. 2 zeros there. And that's not an easy task because of the sine and cosine. So it's going to be easier to follow the envelope curve approach. So I want to rewrite this function y of t in the following form: r e to the minus t over 5 cosine of 8/5 t minus phi. And if I can do that, then I can use the envelope curves here to tell me when it's going to be trapped within 0.001, because the cosine part is never bigger than 1. So how do we do this? We got to find r. I think we went over in class how to do this is that r can be found as the square root of c1 squared plus c2 squared. In this case, we have square root of 0.3 squared plus 0.4 squared. We might have the answer right now. If not, that's fine. Let's work this out. That's the square root of 0.09 plus 0.16, square root of 0.25. That's a quarter. This is a half, or 0.5. 3, 4, 5 right triangle. We could find phi, but I don't really need phi to answer this part of the problem. So what I know is that my function y of t, I can represent as 0.5 e to the minus t over 5 cosine of 8/5 t minus phi, whatever phi is. And so if I want y to be trapped within 0.001 of equilibrium, I can just look at this part here and set up 0.001 equals 0.5 e to the minus t over 5. Why am I setting equal to here? Well, I know that these are exponentials, so they are always strictly decreasing. To find out where they hit the threshold point, they are always smaller than it after that point. So this will be, not little t, the capital T I'm looking for is the t value that solves this equality. We can solve that. Multiply both sides by 2 to get rid of the 1/2, take natural log of both sides, and then multiply by -5. And if we compute this out, we get around 31.07 seconds. So with this particular setup, it would take about 30 seconds to then guarantee that the mass will be within 0.001 meters of equilibrium. That's how you would go about solving this mass on a spring problem involving both setting up the problem with hidden coefficients, as well as using envelope curves to figure out a threshold time for when you get within 0.001 meters of equilibrium.